Hello, everyone. I'm Tengli, and I come from University of Alberta in Canada. I am very glad to share my research work here. The title of my presentation is Neural Network Learning of Robot Dynamic Uncertainties and Observer-Based External Disturbance Estimation for Impedance Control. This presentation includes 5 parts. The first part is background and motivation. Second, our proposed solution. Third, simulations and results. Fourth, the limitations of this work. Fifth, summary and conclusion. First of all, background and motivation. In our previous work, it has been shown that integrating an impedance controller with a disturbance observer can realize an accurate impedance control. However, it only works for robots in free motion, but not in scenarios of physical human-robot interaction (PH/I). The reason is that a disturbance observer always estimates the lump uncertainties and cannot be able to separate any component of it. For the PH/I scenario, without separating the external human-applied force, the method of impedance plus observer will result in the human-applied force being cancelled, thus rejecting human-robot interaction. Therefore, the problem is how to separate the external force out of the lumped uncertainties. To solve this problem, in this paper, we proposed a framework for learning the internal disturbances and thus separating the external disturbances by integrating 3 entities, that is, an impedance controller, a nonlinear disturbance observer, and a neural network model. The impedance controller provides compliant robot behavior. The nonlinear disturbance observer captures the lumped uncertainties, while the neural network model learns to estimate the lumped uncertainties in the training process, thus separating the newly added uncertainties, that is, the external disturbances, in the testing process. In this work, the uncertainty sources are defined as 1. Model error, 2. Joint friction, 3. External constant payload, and 4. External time-varying payload. During the training process, only uncertainty source 1 and 2 are involved in the training data, which means the trained neural network model can only estimate the source 1 and 2 uncertainties. In this way, during the testing process, the trained neural network model is able to separate the source 3 and 4 uncertainties if all 4 sources of uncertainties are involved in the testing data. The detailed procedures in this work are illustrated in this figure. First, a bunch of exciting trajectories are generated. Then, we conduct trajectory tracking tasks for collecting training data and testing data. Note that for training data, only uncertainty source 1 and 2 are involved, while for testing data, all sources 1, 2, 3, and 4 are involved. Then, we train the feed-forward neural network model using the training data, and test the trained feed-forward neural network model using the testing data. Lastly, we applied the trained feed-forward neural network model into a simulated application scenario. There are various disturbance observers and various neural network models available. So, first of all, we need to decide which observer and which neural network model will be used in the proposed framework. In this figure, we compared the disturbance tracking performances of 4 disturbance observers. The results show that the performance of nonlinear disturbance observer, generalized momentum observer, and disturbance Kalman filter are significantly better than extended state observer. Considering that the nonlinear disturbance observer can capture nonlinearities and easy to implement, the nonlinear disturbance observer is selected. For neural network models, feed-forward neural network, cascade-forward neural network, and NOx are 3 potential candidates. These two figures show the prediction performance after they are trained by the same training data set. The results show that the performance of the Knox model is PO, while the performance of the feed-forward neural network and cascade-forward neural network are comparable. Considering that the structure of the feed-forward neural network model is simpler, the feed-forward neural network model is selected. Then, we investigate the effect of dynamic model error on the estimation performance of the feed-forward neural network model when the robot dynamic model error is on different levels, that is 0%, 10%, 50%, and 100%. There are two tracking tasks employed for this purpose. The first one is a simple figure-eight trajectory tracking task, and the second one is a complex harmonic trajectory tracking task. The results show that there is no significant difference among model error levels 0%, 10%, and 50%. In general, the effect of model error level on the feed-forward neural network estimation accuracy is relatively small. A possible reason could be that, for the lightweight robot used in this work, the dynamic model errors are on a relatively small scale. For other heavy industrial robots with dynamic model errors on a large scale, the effect of dynamic model error needs to be re-evaluated. Lastly, we implement the trained feed-forward neural network model in a simulated application scenario where an obstacle virtual fixture is involved. The contact forces between the robot and virtual fixture are presented in two conditions separately, as shown in the figures. Condition 1 has only the nonlinear disturbance observer activated, while condition 2 has only the feed-forward neural network model activated. In the figures, the grey area represents the obstructive virtual fixture, which will exert a contact force on the robot end effector when they are in contact. The green line represents the contact force between the robot and the obstructive virtual fixture. As we can see, the contact force in figure is extremely large due to the fact that the nonlinear disturbance observer escalated the adverse effect of the obstacle virtual fixture, while the contact force in figure B is reasonably small. This indicates that, in condition 2, when only feed-forward neural network is activated, the robot is much more compliant than that in condition 1. This is because the feed-forward neural network in condition 2, as it was trained in the training process, only estimates the internal uncertainties excluding the external ones caused by the virtual fixture. One limitation of this work is that the trained feed-forward neural network in this study works only in trajectory tracking tasks, but not set point regulation tasks. This is because the feed-forward neural network model is trained by data collected only from trajectory tracking tasks. Therefore, the feed-forward neural network model would be capable of working for both trajectory tracking tasks and set point regulation tasks if it is trained by data from both. This will be evaluated in future work. Another limitation is that only simulations are conducted in this work. In future work, we will evaluate the proposed framework through physical experiments. Finally, summary and conclusion. In this paper, we proposed a framework for learning robot dynamic model uncertainties and separating external disturbances by integrating impedance controller, nonlinear disturbance observer, and feed-forward neural network model. In the simulations, by accurately controlling each of the four uncertainty sources, the results showed that the feed-forward neural network can effectively learn the internal disturbances sources 1 and 2, thus separating the external disturbances sources 3 and 4. A simulated application scenario with an obstructive virtual fixture demonstrated the effectiveness of the proposed learning framework. At the end, I would like to thank my supervisor Dr. Tavakoli, and all the members in TBS Lab Group, as well as the funding sources. That is all my presentation. Thanks for your attention.